Right. All right. Well, welcome everybody. As people are joining in, I'm going to go ahead and get rolling with our Ask Mayfield Anything for February. And I'm really excited about this topic that we're going to be talking about with Blair and Lee. And so it's really all about UL 3741, rapid shutdown, and kind of some big changes for the industry as a whole. So we've prepared some slides and we have some points to talk about as everybody's joining, as you're getting settled in. This really is meant to be very conversational. So the idea is for you to submit questions, ask us some of the questions that you have on the topic at hand specifically, but love to hear from you. So feel free to do that. And so let's get moving in. And so thanks for joining. My name is Ryan Mayfield, founder, CEO of Mayfield Renewables. We're a technical consultancy, and we do work across the industry, working with manufacturers and general contractors, EPCs. So we do content strategy, production, education, PV and energy storage education, and system design and engineering. So, we're out here trying to help move the industry along, and so that's a big part of why we do our AMAs, our Ask Mayfield Anythings. And today we have a couple of special guests here. We have Blair Reynolds, energy storage product manager from SMA, and Lee Rothschild, director of engineering from Sollega. Blair's been in the industry since 2007. Is that right, Blair? And
that's right.
You NABCEP certified, and even have a master's degree in PV engineering from University of New South Wales. So that's pretty impressive right there. I like that. And then Lee went to school at Colorado School of Mines. It's been in the industry since 2012. Is doing director of engineering over at Sollega. And so his primary role over there is overseeing project design, engineering, development of new products. So welcome to both of you. Appreciate you joining us.
Thanks so much, Ryan. It's great to be here on your Ask Mayfield Anything.
Great.
I guess I get to ask you anything, right?
Yeah.
Awesome.
Exactly.
There's a question that I've always wanted you to answer for me, and I think this is the right time for it. What is a PV array, Ryan?
Okay.
What is it?
Okay, so thankfully I'm prepared for that one. And so, PV array, this is, and as I've been doing my classes, so for those of you that may know, I've been doing code classes for many years now. I teach a lot at the NABCEP conference, which is coming right up, by the way. I highly recommend folks check that one out. But do the code classes at the NABCEP conference, and one of the things I always do is I try and get people to not to make the mistake that I made, and which was ignore the definition section of code, especially the definitions in 690, because as PV professionals, we all know the definitions, but it's important to read them and to understand them. And so I did put that this slide here. What we're looking at is the definition of a PV system, or excuse me, of an array, and it's a mechanically and electrically integrated grouping of modules, support structure, attached components, all of these things, and attached associated wiring. So what you're looking at there is the actual code language, and it becomes important as part of this conversation that we're going to have with you guys. And because we're going to get into array boundary next, we're going to get into controlled conductors, and we have to know what is part of the array. And so this really becomes part of it. And I probably spend as much time as outside of those writing this definition of reading it and kind of picking apart the language. And it is a little bit vague in some cases, in some ways, and it's a little bit open to interpretation. But that's, I would say, pretty much the way it is in code. So that is going to be our base, what we're going to talk about. And what we're going to present here is using this definition as our array and be able to move forward from there. So as a note, before I move on to the next slide, for those of you, if you have questions, please, if you could put them into the Q&A box as we're going along. There's both a chat and a Q&A. Much easier for us to follow along, get your question if you put it in the Q&A, can get lost in the chat. So please just put those there as we're going along. And again, feel free to put those in there. We do want to be interacting with all of you. So with that, the next section that I want to talk about, or the next thing I want to talk about, is really what we're here to talk about today. And a lot of words on the page, somewhat apologize for that, but it's also important. So we have 690.12, rapid shutdown of PV systems on buildings. That's our title here. And really what we're going to focus on is B2 and number 1 within B2. So B2.1 is really where we're going to put our laser focus in on. And what we are up against is, and we've been doing this for many, many years now, and so we have this requirement to control the conductors within the array, or excuse me, we have to control the conductors, our PV system conductors. And so there's multiple ways we can do that, as we all know, anywhere from using module level power electronics, inverters, by having switches and things like that at different locations to meet these requirements. One of the things that we've quite honestly ignored as an industry up until now will be this number 1, B2.1. And so this PV hazard control system is something that's been in code. As someone who teaches the code, it's been an easy one for me because I can say there's no such thing on the market. So we get to skip it and we get to move on, and we get to talk about the only way that we can meet this requirement at this point. That's changing now. And so we have this UL 3741 PV hazard control listing, and Sollega has gone through, and I'll let Lee spend more time talking about this, but gone through, done the testing, and met those requirements. And so now we have a system that meets the UL 3741. And so we can actually install a PV array system that meets this without necessarily having to install module level power electronics. Lee or Blair, do you have anything you want to add to that one before we jump into the next set of slides?
I'll just say that, 3741, it's a fairly new UL standard. It was only published at the very end of 2020. And so that's by and large why we haven't seen more applications like this come into existence so far. It's because the UL standard, which of course defines the different test scenarios, wasn't published. And so now that it is, though, we're starting to see the very first applications and products start to utilize and take advantage of this option, which has been hiding in plain sight in the code for the last few code cycles. So finally, we can now take advantage of this.
Right. And one of the things, and you two may touch on this again in a bit, but one of the things I did want to mention, and Blair, I've heard you say this in conversations before, but PV systems, especially PV systems we're installing today, they are inherently safe. They are not, when done to code, and maybe that should be the preface of that statement, when installed to code, when installed properly, they are inherently safe. So somebody going up and touching a system, the HVAC person up on a roof, the kid retrieving the Frisbee, all those things, there's no inherent danger associated with it. And this picture is actually an interesting one in the sense that we see the firefighters using the array as kind of a brace, and even in a damaged state, they're obviously not getting injured. We don't know what's going on with that array, so it could be that could be a microinverter system and it's completely off. We just don't know, but nonetheless. And so UL 3741, what it's trying to address are hazards associated when a PV array is not, when it's been damaged, when it's in some sort of state of damage, in order to, what risk are we placing the firefighters, first responders at when there are levels of damage. And so 3741 had to establish what those levels of damage are and be able to give manufacturers something to test too. So that's kind of the big thing here is, really want to drive that home. you put a PV array up on a roof, and it's not like all of a sudden things are, you're just asking for trouble. It's in these damage situations, and that's why this is all about firefighters. And it's even in the charging statement of code, talking about reducing shock hazard for firefighters. So just wanted to kind of, I guess, climb on that soapbox a little bit and just kind of point out those different points. So with that, I'll turn it over to Blair and Lee here and kind of let you guys talk about the system specifically.
Yeah, thanks so much, Ryan. Kind of along that same vein that you were just describing, my next slide here coming up, I have, of course, an important legal notice, but here, as you were mentioning, PV systems, when installed according to code and according to best, practices for workmanship, really are inherently safe. I would say modern PV systems, and I say modern because if you look back, 15 years ago when we were really started to see the very first boom, in the US market of these rooftop systems going in, we didn't have such built-in safety features as are now required by code, such as ground fault detection or arc fault detection, for example. So, I will say that the safety has only improved over time, right? And with modern transformerless PV inverters especially, there are multiple layers of safety. First and foremost, transformerless PV inverters have daily insulation resistance measurements and a continuous residual current detection. And so what that means is that a ground fault, if and when it does occur, it will be immediately detected and the inverter has to react to that. Secondly, transformerless PV string inverters isolate the array from the ground reference after you disconnect the AC or you throw the AC disconnect switch. And so what that means is that a single point of contact to a live conductor, a live circuit, poses no risk to a first responder, to a firefighter who's interacting with that array. The firefighter would actually have to put themselves in that path of current, meaning they'd have to touch a live conductor and a path to ground, like a grounded metal part up on the roof, for example, in order for them to be inserting themselves into that circuit. So 2 points of contact are required, not just a single point of contact. And then lastly, I'd say systems built today that maybe are different than how we were doing it 10, 15 years ago, by and large are required to have setbacks, walkways, specifically for first responders, for firefighters to move around the roof when there is an emergency, and to give them locations and opportunities for where they can vent the roof, chop holes into the roof to let the hot gases out as needed. But there really isn't a need for firefighters to actually be chopping through the PV modules, because they have, international building codes and other local codes and standards. They have these setbacks and walkways which are designed to give them that access that they need. So I'll go to my next slide. And here just a couple more points to consider about, again, sort of the inherent safety that exists. According to the NFPA and other codes, only qualified personnel are allowed to work on a PV array, right? And so technically firefighters, if they're not licensed to do so, really shouldn't be removing PV modules and really have no business in intentionally chopping a hole into one, as I mentioned before. It's kind of like, if a firefighter was wanting to vent a roof, but there was a piece of HVAC equipment right there, right? They're not going to sit there and try to chop through that HVAC equipment. That just doesn't make sense. Additionally, I'll say that it's really, the presence of voltage in the array is not dangerous. I mean, it's not voltage that kills, right? It's current that kills. And specifically, it's becoming part of that current path, like I was mentioning before, 2 points of contact. And so what really matters is the continuous insulation of that DC circuit and the monitoring thereof, which, as I mentioned before, is inherent in all modern transformerless PV inverters today. So what it comes down to is reliable wire management and good workmanship really are the basis for that continued insulation. And that's why Sollega is here with me today, because the mounting system really does play the key role in, defining how the wire management is maintained, a repeatable process in order to keep your cables from becoming damaged, rubbing against sharp objects on the roof and that sort of thing. So reliable wire management, maybe this shouldn't be a surprise, because it is, of course, one of the first things inspectors look at to kind of get a sense of how well a system is installed. Reliable wire management and good workmanship when it comes to wire management really adds so much to the overall safety of the PV system, especially in the event of a like you said, a damage, if there's damage to the array, those kinds of scenarios.
Well, and it may be worth pointing out here, and hopefully I'm not stepping or jumping ahead of you, but so the whole 3741, I would encourage folks, first of all, you can go onto UL's website, you can create a free account, and you can read the entire 3741 listing for yourself. Part of it's riveting reading, and then part of it will put you right to sleep. But it's interesting, and I think everybody on the call is obviously interested in the topic, and it's something that you can go and look at yourself. But I think a big part of what, again, we're having to define what those hazards are and find some way of testing for those. And so this is 3741 is all about trying to account for what the hazards really are in that exact scenario. And so they went through a very thorough analysis of what is the protective gear that the firefighters have to wear per OSHA anyway, what it's not electrical gear, but what are the inherent safety pieces of it. And so there's a lot to it, and it's all about, and it really comes down to wire management, like you were saying, it seems like, in terms of keeping the firefighters out of that current path.
Yeah, I mean, 3741, as far as UL standards go, it really is in sort of a league of its own. I mean, it's pretty far out there. They basically take an FMEA approach to try to create this a risk matrix, and they score all these different possible scenarios differently. But I mean, they have, like you said, they consider the insulation of the standard firefighter PPE, especially in wet conditions, the worst case scenario. They actually look at the human skin resistance and how it's different between men and women. Again, taking the worst case scenario. They have a series of tests that are designed to simulate a firefighter tripping and falling into the PV array, the glass in the array, tripping and falling with or without an actual tool strapped onto them, or like an axe in their tool belt. And so, yeah, I mean, what it comes down to, though, is that systems that are tested and certified to 3741 are specifically evaluated for safe interaction with firefighters and first responders. And that really is the key here, is that you're not compromising on safety, because actually through the development of this standard, we actually have a very reasonable and practical way to evaluate the overall safety of the system for interaction from the firefighter community. And so here, as I was mentioning before, there's inherent safety already built into the array. But it would take multiple faults and damaged, firefighter PPE in order for an actual, risk of shock or electrocution occurring. So UL 3741 really is designed to account for the likelihood of those specific types of faults from occurring. Now, I know that you touched on the code sections a little bit already, especially 690.12. I have sort of my own way of presenting these concepts. I tend not to use the words rapid shutdown, because it's first and foremost, I think it's sort of a contradiction. It's not very terribly rapid. It's not necessarily a shutdown. But what it is all about is controlling conductors, specifically conductors outside the array boundary and conductors inside the array boundary. Now, the reason that I gave you that loaded question initially is because I really want to emphasize that the NEC definition of the PV array. Clearly, the NEC states that the PV array does include the support structure that is definitely part of the PV array. You can't argue that. It's clearly spelled out in literally black and white. So the PV array boundary, therefore, is a 1 foot projection from the furthest most point of the PV array. So the PV array boundary can extend 1 foot from, for example, not just the module, but also the mounting system, right? Because the mounting system is a fundamental part of the PV array. Great. So just a brief recap. You've got 690.12b1, controlling conductors outside the array boundary. That's mandatory. There really is no flexibility. The code says less than or equal to 30 volts within 30 seconds. No other options or exemptions for rooftop PV, that is. But then we have this section 690.12b2, controlling conductors inside the array boundary. And as you mentioned before, there are multiple ways that you can comply with this, but by and large, we have, as an industry, been using the second of those 3 options, which is essentially MLPE. I mean, what the code actually says is less than 80 volts within 30 seconds, but by and large, that means putting some kind of switch behind every module or grouping of modules in order to accomplish that less than 80 volts. But who says that 80 volts really is the definition of, or the threshold of safety, especially when you consider that it really is, it's not voltage, it's current, and becoming part of that current path that actually exposes a first responder, a firefighter, to an unsafe scenario. So 80 volts is sort of arbitrary, and that's definitely one of the learnings in the development of the 3741 standard, that when you actually factor in the capabilities of typical firefighter PPE, 80 volts is ultra conservative. So I'll briefly touch on the third of those 3 options for complying with controlling conductors inside the array boundary. It basically is an application very specific for BIPV, some kind of roof embedded solar shingles, for example, where you have no metal or exposed cables whatsoever. Of course, that wouldn't work with standard format PV modules, framed modules. So the first of those 3 options is the one that we're going to be talking about here today. A UL 3741 certified listed PV hazard control array. So here on the right-hand side of the screen, just as a reminder, these are kind of the visual depictions of PV array boundaries. The PV array boundary, of course, doesn't have to be a solid rectangular shape. It can have little dips and cutouts as needed, depending on where the equipment is located on the roof. PV array boundaries can overlap, which is a very important concept to remember. So essentially, you could have a 1 foot projection from the furthest most point of a PV array on the south side of the roof, with overlapping 1 foot projection of the PV array boundary from the north side of the roof. And you basically have a 2 foot gap between those furthest most points. And that technically is still part of the contiguous PV array boundary. Right. All right, now that we got that down, let's go to the next slide. All right, so here is pretty much what we have developed between our 2 companies, Sollega and SMA, based on SMA's leading flat roof commercial string inverter, the Core 1, available in 3 different power classes from 33 kilowatts all the way to 62.5. What we are doing is we have the equipment inside the PV array boundary, which clearly is the modules, it clearly is the mounting system and other components as needed. That equipment is certified, tested, certified according to 3741, meaning that it has been verified to be safe for firefighter interaction. Therefore, we are complying with 690.12b2 with that first of those 3 options. Now, that's fine for the conductors inside the PV array boundary, but of course, we have to control the conductors as they leave the PV array boundary, right, as they exit. And that's what the Core 1 inverter is doing. The Core 1 inverter in this application is the rapid shutdown device. As long as you install the inverter within a 1 foot proximity of the furthest most point of the PV array, which of course can include the mounting system, And in the case of Sollega, the mounting system actually extends 18 inches beyond the edge of the frame of the PV module, right? So it's doesn't mean the inverter has to be within 1 foot of the module. It can be 28 inches, 30 inches away. So that's essentially what we've done. This is a fully code compliant with NEC 2017 and 2020, fully code compliant application, which meets the code requirements for controlling conductors inside the array boundary and conductors outside the array boundary without any module level switches or actually any other rapid shutdown devices at all.
Right, and I'll get a little nitpicky on you there. And so it really, I mean, it's the controlled conductors that we have to have the controlled conductors within the array within the array boundary. So really that, that 1 foot is kind of, in this case, you have your quick connects coming into your core one. And so those conductors need to be within that 1 foot array boundary. So the inverter doesn't have to fully be, and I just kind of a clarification, I guess, as much as anything, the inverter doesn't have to like wholly sit inside that 1 foot array boundary. It's those conductors that we're really concerned about.
Exactly. Yeah. The conductors that of course plug into those, the DC input area
DC input
on the
conductors.
Yep. Exactly. All right. So
I knew you on that, but
let's go to the next slide here and show you some actual examples of how we could apply this application. So first and foremost, contiguous arrays, where you have these sort of large groups of modules all sharing a common PV array boundary. Those are the kinds of applications that really can take the advantage of this. I would say this application the best. And so here are a couple of examples. Tesla Gigafactory, that's a huge 70 megawatt rooftop array. Also Mandalay Bay Casino. What these two systems, I'd say both have in common, they've got large roof space and luxury of being able to, group your modules together in these large clusters. And then essentially by locating your inverters in close proximity, the inverter is then acting as the means for controlling the conductors as they leave that array boundary. In both of these scenarios, I really don't see an actual benefit from a production standpoint of putting any kind of module level maximum power point devices on each of these. There really is no serious shading features. So just throwing an MLPE up there for the sake of code compliance. Now I would say we finally have another option that exists in our tool belt, especially that we can take advantage of these large flat roofs. Let's look at a couple of examples of how this actually works. So here is a stringing design on a real system that was installed with Sollega and the Core 1 inverter. The Core 1 inverter has not been mounted yet in this picture. It's kind of hanging out right next to that middle HVAC unit. But here, all of the modules that are connected to this single inverter are basically split out into two array boundaries. That may not be exactly obvious at first, but when you look at that gap that exists between the southern array and the northern array, where it has a strip of conduit running right through it, when you look at that gap is not greater than 2 feet. So you have a projection of, like I mentioned, coming 1 foot from the southern array, projection coming 1 foot from the northern array, and that distance, that gap, does not exceed 2 feet. Therefore, that is still a contiguous PV array boundary. It really is that grouping of modules, that string of modules up in the upper right-hand quarter that's sort of orphaned. It's kind of sitting out there on its own. And so as a designer of this system, if I want to take advantage of this application and reduce or eliminate the need for MLPEs on this system, I have basically two choices. I can either consider relocating that subarray down the roof a little bit closer to the location of that where that inverter is installed, or I can redistribute those modules somehow elsewhere on the roof in close proximity to the other modules, therefore making a solid contiguous array boundary. If neither of those options are very practical for whatever reason, you do have the option of putting MLPEs on only that portion of the subarray, right? So you can, in the case of SMA, we use the SunSpec rapid shutdown protocol. SunSpec devices can be installed on only that subarray, whereas all of the other modules that are part of that contiguous array boundary that's shared with the DC input area of the Core 1 inverter will not require any MLPE. So definitely some significant cost savings advantages. Let me just point out before we move on, though, I know I've been talking about Sollega. This application actually also applies to the Iron Ridge BX mounting system as well. So for those of you that are familiar with that product line, this exact same certification and application works for the Iron Ridge BX mounting system as well. All right, next slide, please. Yeah, here's another example of kind of how you can think about laying out your PV arrays on the roof while still maintaining, appropriate walkways and setbacks for firefighters to be able to, conveniently move around. You can see here, those cones that are being placed around the perimeter of this array. There is a 4 foot or so, setback around the parapet of this roof. If I look at the kind of that section of the roof where they're still laying the modules, you'll see that there is a little bit of a gap that's going to exist there based on this current layout. Now, again, as a designer, I have those options. I can try to bring those two separate array boundaries closer together such that they're within 2 foot proximity. Or I can try to get a little bit more creative with how I lay out my array on the roof. Or I can decide to put rapid shutdown devices, MLPEs, only on the portion of the array that is not in sharing the same array boundary as the inverter.
Cool. Great. I'm going to real quick. I see we had a question come in from Chad when it's asking about this will only work on totally flat arrays, and to that point for these specific systems, for the Sollega system and the Iron Ridge system that you mentioned, those are the systems that, at least I know of, that have been listed to the 3741 standard. And so those are flat roof ballasted array systems. Not to say that a pitched roof racking manufacturer won't have or doesn't already have, I don't know of any, a UL 3741 racking system. So for what we're talking about today, yes, these are flat roof specific, but there could be 3741 pitched roof racking systems available.
Yeah, definitely. And I'll just say that this technique that we've applied, it really can be, broadened to even traditional rail-based mounting systems, even metal mounting systems as well, because it really doesn't so much. It's not so much a matter of how much metal is on the roof. It really is a matter of how well your wires are managed. The technique that you apply to your wire management is really kind of the key to creating a repeatable and reliable wire management technique. So definitely, I expect that this application will continue to grow into other different types of mounting systems and other applications as well. I mean, the code certainly affords the opportunity to use this in a residential application also. So definitely think what was important, the most important thing about this project was that we were able to prove, based on empirical testing, that up to 1,000 volts within the PV array boundary was deemed to be safe for firefighter interaction. That really is sort of the groundbreaking, I would say, or disruptive learning here in this project, is that who says 80 volts is the limit of safety? We've been able to prove that 1,000 volts in the PV array boundary is safe for firefighter interaction. Right. Let's go to the next. Yeah. And here I'm going to pass it over to Lee to talk a little bit more about the unique wire management techniques of the Sollega mounting system.
Lee, it sounds like you're muted. No.
Hello?
There you are.
All right, I guess I'll have to yell a little louder.
There you go. We won't be offended.
No worries. So for those of you familiar with our racking, we are manufactured out of nylon. So it is an inherently non-conductive system, which was one of the reasons we had gone through the certification process for this in the first place. It seemed like a likely direction to go. As he explained earlier, Blair explained that a lot of the control of the conductors within the array is pretty significant and important to getting the certification. The way we run all of the wires throughout our system are using a nylon wiring clip that is clippable to either the panel frame on the interior edge or on any of the open edges on the racking, which there are a lot of. The air gap that is present in between the wires and the racking and any metal on the system, in this case, mostly the PV panel itself, is what gives us the ability to create the safety that we needed in order to pass the UL testing. So the nylon clips that we use create about a natural 1/2 inch to 1 inch gap between any of the metal on the system and any of the metal around the array. You can see in this image here, a home run is being run along the underside of the racking. We leave enough lip on the outside of the racking so that way you have sun protection from the wiring and a direct route along the perimeter of the array to keep a significant gap between the wiring and the panel frame. If you could pop over to the next slide really quick. So the general benefits that you get from using the racking are, as I said earlier, it's a non-conductive system. We manufacture it out of a nylon with a reinforced glass fiber inside of it. There are no sharp edges. It does absorb impact. It is a flexible system. So when a lot of the testing was done, a lot of the scenarios involve a firefighter crashing through a panel. A lot of the absorption of that prevents further destruction to the panel as well as to the panel frame. It's a lightweight system. We're Class A fire rated, and all of the actions needed to apply the panels to the racking are top down and easily accessible. Can you guys still hear me?
Oh, yeah.
Okay.
And so,
Go ahead. I'm sorry.
well, I think we actually have some real case studies that Mayfield has prepared for us here to help demonstrate the potential cost savings from taking advantage of this application.
Yeah, do you want me to talk this one through, Blair?
Yeah, go for it, Ryan.
Yeah. Okay. So what we did was we were looking at some actual systems and went through and really just looking at applying this 3741 with what we've been talking about, putting the inverters essentially at the array edge, within keeping the conductors within the array boundary. And so we went through and have a system using some traditional SolarEdge type inverters. And in this case, because of the MLPEs and because of the way that rapid shutdown is initiated, the conductors are all going to be they're going to meet that less than 80 volts in less than 30 seconds within the array boundary upon rapid shutdown initiation. So the idea that now you can run those DC conductors across pathways, you can run them across walkways, array to array, you can completely do that. And so that's what we've been doing for a long time. And quite honestly, it's probably what a lot of people out there in the audience are doing now, using MLPEs. And so taking that exact same array and breaking them into individual, that exact same system, I should say, into these multiple arrays, and applying putting the inverters within there. So what we're looking at is these individual arrays, all of the conductors associated with those arrays are going to inverters that are within 1 foot of that array boundary. And again, I just want to be really clear, the array boundary, I saw a little chatter in the chat box, and of course it got lost in everything. The array boundary includes the racking system. It is explicitly put in the definition of the array. And so it's not a technicality or anything, it's part of the definition. And so we are able to include that 1 foot boundary, including the racking system. So that's what all of these systems did, using the same module count. And what you can see in this system, and I'll kind of point this out, you see we have 3 different core 1 inverters, and really what that's a function of is keeping that DC to AC ratio nearly equivalent on the systems, but also, some of these arrays are a little bit bigger, some are a little bit smaller. And so it's a matter of being able to maximize your DC to AC ratios is really what that is a function of. And I did notice somebody asked the question, this would be a good point we don't have any dimensions on this array, but somebody asked what those dimensions were on commercial rooftops for fire codes, things like that. 150 feet is kind of your first working dimension. So 150 feet any direction, you're going to have to create a pathway and ways for firefighters to move around that roof. And then depending on that pathway, minimum 4 feet. But if you only have a 4 foot pathway, then you have to give cutouts, and I forget the exact distance, but there's some requirements of having cutouts. So you have to have another 4 foot by 8 foot, basically cut out along that pathway that's not in the pathway. So 150 feet is kind of that magic number, and then minimum 4 foot pathways in between. So that 4 foot pathway in of itself is going to kill any contiguous array that we were talking about with Blair. But so back to this, and so went through. We used a software PV bid and analyzed these 2 systems. And really, what it came down to is, so PV bid is an estimating software, so we're looking at the cost differences. And so what you see here are the results from that, running those 2 systems in that specific way that we did to maximize the use of the arrays as they stood, so that we're not having to add. Blair mentioned you could add MLPEs on an array or a section of an array that's associated with a different inverter. We went away. We didn't do that. We were doing it such that this whole UL 3741, the inverters are within that 1 foot boundary. The conductors are in that 1 foot boundary, and so it becomes, I would say, a relatively bulletproof application to 3741. You're not trying to stretch those limits of having conductors more than 1 foot from the array and calling it part of the array boundary. And that's maybe a topic for whiskey at NABCEP. But the results here is what we'll kind of show you here. The bottom line is that at the very on the left there, showing about a 4.2 cent watt increase on the solar system. And so if you look at all those, it's just a function of the different components. And so you can see how granular all of these costs were broken down. These costs also include labor built into those. And so that's an important aspect of it. And so there's some big gains. The line inverters includes the MLPEs in this case. And so there's some big gains there in terms of not using the module level power electronics. But as Blair mentioned, you have more inverters, you have more AC runs, and so it eats into some of that. But still, the net result is a cost positive.
Yeah, and I think it's interesting here. We're 4 cents a watt maybe doesn't sound like much, but in a 3 megawatt plant, we're talking about nearly $130,000 in actual savings for the installer here. And when you factor in, margin markup, that sort of thing, taxes, the cost delta for the end user, the owner of this system, is actually more on the order of 5 cents a watt. And again, these were systems which were originally let's say, designed around an MLPE-based solution. So definitely, I think there's room for further optimization if you know going into your project, you want to take advantage of this. One thing that isn't considered, however, in these kind of cost roll-ups is the impact on the overall O&M, the lifetime, maintenance cost of the system. By not having MLPEs distributed throughout the entire rooftop array, you definitely have less likelihood of electronics failing over the life of the system. So definitely an important consideration as well.
Yep, exactly. Agreed.
Cool. Well, yeah, just to kind of wrap up on a couple of key benefits, and then we'll open it up for some questions. Again, if you want to ask a question, please use that Q&A feature, not the actual chat, but the Q&A feature here on Zoom. So as we just demonstrated in that cost comparative example, the power conversion costs can be reduced by more than 8 cents a watt. But in that specific example where we had the inverters going from more of a centralized location to a distributed across the entire roof, those cost savings were somewhat eroded just by the additional especially the AC wiring. But those costs did not include any consideration of the lifetime O&M and the cost of rolling trucks to replace failed MLPEs. Furthermore, this really is a far more reliable system design because you don't have the opportunity for these DC to DC converters within your PV array to fail over time, right? So higher system uptime, it's a far more reliable design. And part of that is because you virtually eliminate the opportunity for connectors to be mismatched without having MLPE on the roof. You're simply plugging module to module, plus into minus, right? And so there's actually a 65% reduction in the number of connectors on the roof, which I think we all should know is one of the weakest points. The highest potential points of failure within the roof is the connector itself. So by getting rid of a large quantity of connectors, you do have a much more reliable system design. One other thing that I think is really cool about this application is that it enables you to use PV modules, which are traditionally only used in utility scale or large, ground mount applications. And that is because those modules, I'm talking about 500, 600 watt plus modules, tend to have higher currents beyond 15 amps, which it seems to be kind of the current limit of MLPE's input capability. So by being able to utilize these utility scale modules, oftentimes they're bifacial, they have high currents, lower VOCs based on the 210 millimeter wafer size, for example, M12s. You are able to realize some potential cost savings there on the module side as well. And that using higher current modules, as I mentioned, those tend to have lower VOCs, lower voltages, so you can actually string more together in series, so longer string lengths. In this case, in my example here, based on a Trina 555 watt module, that's more than 13 kilowatts per string.
That's interesting. I guess I hadn't really, that's a great point. I hadn't thought about those modules getting opened up now.
Yeah, just more room for design creativity and being able to take advantage of those large format modules in your commercial applications. I'll say that definitely there is less wire on the roof, less DC conductor if you don't have MLPEs. Believe it or not, a dual input power optimizer has about 26 feet of cable associated with it. So every module pair, you can eliminate 26 feet of DC cable, and therefore reducing the voltage losses, the voltage drop. That ends up being about 200 watts of extra power, free power for each string in full sun. As I mentioned before, far less lifetime service risk. Your O&M costs should definitely be a serious consideration when you're considering this application, how you can reduce your O&M costs. With the SMA Core 1 inverter, we do have built-in IV curve tracing, this really cool feature that we launched last year. So IV curve tracing is far above and beyond the amount of granular detail that you get for diagnosing your system remotely from a a module level monitoring device, right? A module level sensor. But actually being able to look at the entire string IV curve, you gain a lot more insight. And that capability coupled with SMA Smart Connected, which is a proactive monitoring system where you actually have real human beings looking at alerts and fault codes that might come through and proactively shipping replacement materials, RMAs, that sort of thing. Again, it really is a best in class in terms of the remote monitoring and diagnostic capabilities there. And then lastly, I'll just point out, while we are establishing pretty good end of life recycling options for the PV module, which is absolutely great, it needs to happen. There really is no opportunity for a circular economy when it comes to MLPEs. These devices are largely plastic. They are fully potted with a silicone around the circuit boards to prevent them from any kind of moisture ingress. But what that means is that this isn't e-waste. I mean, it really isn't. There really is nothing of value that can be extracted from that product at the end of its life or at the time that it fails. So by getting rid of the MLPs on the roof, you just have far less waste as a result of your system. All right, I think that is a wrap. I think we've, yeah, here's our contact information for your reference. Again, I'm Blair, and I'm here with Lee from Sollega. Feel free to reach out if you have any other questions that we're not able to answer as we open it up.
Yeah, and I'll go one more, and there's some contact information as well. So we're getting some great questions, and so I think this first one, Lee, I'm gonna point it to you. See if I might have to. There's lots of questions in here. So the listing, the questions on the UL 3741 listing, does that apply? How does that apply? Is it to the racking system specific? Is it getting paired up with the inverter? How does that appear? And I guess for question number one, is it Sollega's listing? And then how do power electronics get involved there?
So it is a grouped listing. So it does include the racking, inverters, as well as panels. So it's listed as a set, kind of similar to 2703.
Okay.
We do have independent listings as companies.
So does that mean you have to get a certain classification of modules to meet this? I mean, we have like fire class ratings and things like that. So how do you know, how does somebody out there designing a system know that the modules and the inverters are compatible with for the listing?
So there will be UL listings on at least our website. I would imagine SMA has probably some documentation as well. We do have an expanding list of panels that will be involved in it. We do treat it similarly to, like I said, how we would do 2703, where you test certain types of frame types, backing types, and when you get panels that fit within that kind of corridor, it's just a certification letter, usually between us and whatever ETL or UL that we happen to use for the cert. So
okay,
getting panels added is a pretty easy process.
Okay. And so then as far as the power electronics, I know we have Blair SMA here. Are there others that, folks would be able to look at using with this system?
At this point, I think we are just listed with SMA's products, but I think we're looking into expanding on that. It is going to be part of the UL process.
Okay.
That's right. And so basically, one of the lines of questions has been, what sort of proof or evidence do I give my local AHJ? There will be a certificate available, UL 3741 certificate from Sollega. It references the different module types. It references the Core 1 inverter as the PV rapid shutdown equipment. So one certificate, which you can point to along with 690.12 B21, which clearly states in the code that this is an acceptable means for complying with controlling conductors inside the array boundary.
Great. There's a excuse me, question came from Conti Monroe, somebody known for a while. Thanks for joining, Conti. And essentially he's pointing out, for those of us who don't like putting string inverters up on the roof, is there any way, are there any products, basically string level disconnect products that we can incorporate within that 1 foot array boundary in order to remotely locate those inverters? And Blair, I'll give you the floor on that one, because I know we've talked about it. And so what do you guys have?
Yeah, so today you can, I think the best application of this technique today is by co-locating the inverter within the array. But the SunSpec rapid shutdown standard that we use in all of our string inverters has recently been updated, and it does enable string level devices to participate. So I do anticipate that in the near future we'll see more string level options coming into the market as well. So in the event that you can't co-locate the inverter, in the event that you do want to put the inverter somewhere off the roof, there will be options that exist, is the short answer, for controlling the conductors as they exit the PV array boundary, because that's basically it'll meet that less than 30 volts within 30 seconds requirement.
Yeah, and so that's what I was imagining, and as we've been looking at it, the application of this exactly, and that could even get into, even if you do want to have the inverter up on the roof, but you have a separate array that's 10, 15, 20 feet away, you could add a singular device as some sort of a switch in order to meet SunSpec that the inverter, exactly, when the inverter loses AC power, it sends that signal. So it serves that same feature. So yeah, so that's more, I guess we'll just see that as the industry is evolving and meeting these products for their requirements. Let's see. There was another one, sorry. Question on somebody heard, William said he heard Iron Ridge mentioned. And so the 3741 is for non-metallic mounting only. And at this point, it's, correct me if I'm wrong, Lee and Blair, it's the Sollega, the FR. Is it just the FR 510?
For us, it's the FR 510. For Iron Ridge, it's going to be the BX system.
Right.
BX system.
Both tilts.
And
okay.
But just to restate, this application can certainly be applied to other types of mounting systems, right? It's not at all unique to this combination of equipment, and we really are hoping that it just, as our industry continues to grow and evolve, giving the installer community more options for complying with code that don't compromise on safety. And if you can continue to drive the cost down of the system and make design systems that are more reliable, that really is a win-win scenario.
Yeah. Chris Klingo is asking what the maximum system voltage is that's allowed for the listing, and is 1,000 volts ?
1,000 volts.
Yeah, and that's really driven by the rooftop. The limitation on commercial rooftops is the 1,000 volts, and so and then of course on ground mount systems we're exempt from rapid shutdown for those controlled conductors. So really probably not going to see anything needed to be greater than 1,000 volts on any of these systems. We're running up right at the top of the hour. See, Damien asked, can we get a free copy of the UL standard? You can go create an account on the UL site, and they have a reader. They have a free reader available, so you can go on that and look at that. And then let's see. Sorry, I saw one other one that I thought we could answer quickly, and I lost it. So there's a lot of questions. We weren't able to get to all of them. I kind of knew that was going to happen. So you have all of our contact information here. If there's something that we weren't able to get to, feel free to reach out, ask us those questions. Blair and Lee, thank you so much for joining. This is great. I'm really excited to see this. It's a huge advancement for the industry. So I really appreciate you guys taking the time, joining us here and spending the time with us.
Thank you so much, Ryan. It's a pleasure.
Thank you very much.
Great. And thank you to all participating. Really appreciate it. And we'll see you next time on our next AMA.